This is an introduction to the earthquakes of Western Australia and the monitoring of seismicity within WA. Here we see a recording of a local earthquake. We see the P wave arrivals, followed by the S wave arrivals, and then the surface waves. These are the ones that people feel. And this is the evidence that we do have big earthquakes in Western Australia. This is an aerial photograph from the area of the Meckeringa earthquake of 1968, where we see 2-metre fault scarps. Earthquakes happen along plate boundaries. This map shows the plate boundaries of the Earth in black lines and where earthquakes happen in the red dots, and you can see there's a distinct correlation. However, there are some earthquakes which happen within these solid plates and are known as intraplate earthquakes. Australia sits on the Indo-Australian plate. It's moving northwards at about 7 centimetres per year, as shown by the little black arrow. And that's actually quite fast for a continent. And inside Australia, we have intraplate seismicity, particularly in southwestern Australia and up in the Broome area. Let's have a closer look at the forces acting on the Australian plate. To the north, we have the collision with the Himalayan zone. Yes, forces that far away do have an effect on Australia. And then closer to home, we have the Australian plate going down underneath these collection of plates to the north of us, while sliding past the New Zealand system to the east of us. And a lot of this push is coming from this spreading ridge to the south of us. So let's have a look at the state of stress within Australia. These black lines show the direction of the stress. And we'll note that it's actually an east-west direction, mainly in Western Australia, which is not the same as the direction of motion of the plate. So most of these mechanisms, or the state of stress, indicate that we're getting thrusting. We're getting a lot of compressive stress. And a thrust mechanism is where one side of rock is thrust up over the other side. We also get strike slip, where the two pieces of rock slide past each other. The alternative is a normal fault, which we don't see that many of, where one side of rock slips away from the other side. We mainly get thrusting, maybe with some component of strike slip in it. How does these stresses manifest themselves in the Australian landscape? If we look at the neotectonic period, i.e. that is since about 3 million years ago, or when the current stress regime set in, we can have a look at the faults created in that time. If we look at the younger side of Australia, which is the eastern side, we see quite a lot of long fault scarps, again perpendicular to the compressive stress, and this has a lot of building topography in this area and quite high erosion rates. In Western and Central Australia, that's the much older parts with Archean and Proterozoic rocks, we have a much subdued topography. We have a lot lower erosion rates, but we still do have fault scarps. Now, to get a fault scarp of about 2 or 3 meters offset, we need earthquakes of at least magnitude greater than 6, which is pretty large, and maybe more than one of them to get a fault scarp like so. We haven't really done a huge amount of studies on this, so that's an interesting area to go into. We've had, since 1916, people have noticed at least 11 surface rupturing earthquakes within WA. So let's have a look at the seismicity closer to home. So this is a map, these little green spots are the earthquakes within WA, and we'll see we have a lot down in the southwest, and we have quite a few up in the north in the Broome area. Swarms of earthquakes are very common down in the southwest. Up in the northeast, we get an aftershock sequences. What's the difference? Swarm events are where we have a lot of events of much the same size, and they just rumble on continuously. And these swarms may go for several years, maybe 7 or maybe 20 even years. Up in the north, the Broome sequence tends to be an aftershock sequence. We have one large initial event followed by lots of smaller events, and hopefully they'll die away in the end. So we have a lot of earthquakes around the beacon, and I'll go into a little more detail in there a bit later. We can see that from this picture, this is a picture after the Meckering earthquake of 1968, where it completely disrupted the railway line and destroyed a lot of buildings within that area. And here we've got some significant earthquakes within WA, and as many of them are within living memory, some of you may have felt them. So let's have a look at this swarms sequence in Caddo. This Caddo and Corrigan area, there's a lot of swarms coming in here. We've got about 44 noted areas where the swarms occur, and we're trying to work out, I'll come into how we're doing that later, a bit more detail on what's going on there. Another area where we get a little swarms are in the Norseman area. We've had at least 4 events since 1985 in that area, followed by lots of smaller events. Another area of clustering of events is in the Kalgoorlie area, and there's always the question, is the mining have anything to do with the number of earthquakes in there? I'm not even going to touch on that. So just have a little animation from the Broome event. Have a look at the main 6.6 earthquake, and as we click through the next 24 hours, there were at least 30 events. You can see the sizes are getting a little smaller, but there were at least 30 events of magnitude greater than 3. So, how do we record earthquakes in WA? There are 2 main organisations recording earthquakes, Geoscience Australia, which runs the Australian National Seismograph Network, and these are denoted by the orange squares, and the seismometers in schools programs are denoted by the orange triangles. You can explore more of these in on those 2 websites. These all send data real time back to Canberra. So if an earthquake happens, it's detected automatically, and an initial location is put out really quickly. And you can see these on the website, Earthquakes at GA. They have the details, and if you felt one, you can report it as well. And there's some pictures of the seismograms recorded at stations which detected that earthquake. So to assist with the recording of earthquakes, and I mentioned in the Wheatbelt, the Geological Survey has this year just added 3 more stations in the northern Wheatbelt, 1 in the southern Wheatbelt, and 1 in the Kalgoorlie area. And hopefully this will help us delineate earthquakes better. So how do we actually record an earthquake? So this is a wonderful old instrument, a seismograph, which is basically a weight on a spring. So when the earth moves, that weight stays stationary, and then this causes relative motion between the seismograph and the pen, and a trace is recorded on the paper. Of course, now it's all digital. We went digital, the WA network went digital in 1995, but they are glorious instruments. Earthquake monitoring started in WA in 1957 with the opening of the Mundaring Seismic Observatory. This was added to the Perth Observatory, which monitored meteorological data and kept standard time for WA. The original seismograph is a weight suspended above the paper scroll, as we see here, and when the earth moves, the pen moves relative to it, and we get the ground shaking recorded by the scratchy line. We had the next seismograph was installed in 1964 in Kalgoorlie, and has since been replaced by the Kambalda station and the Meekatharra event station. Then we have stations in the 80s at Ballindu, Calaberrin, Rocky Gully and Forest. So what's actually in those stations? Most of them will have a seismograph here, and that's a broadband instrument which records a wide range of frequencies, and an accelerometer which records the high frequency ground shaking, the strong ground motion, and this is really important for working out building codes. It's all recorded on this set of equipment and then sent by modem back to Canberra. This is an example of a little field site, one of our semi-permanent sites in the Wheatbelt, and we can see the instruments being buried in these buckets, the instrumentation here, and it's all powered by a solar panel. How do we actually locate an earthquake? At each station, the first arrival is the P wave, followed sometime later by the slower S wave, and the distance between these two wave arrivals as an indication of how far away the earthquake was from the station that recorded it. So if we pick up the station and then plot a circle around it as to how far away the earthquake was, and then look at some other stations which recorded the same earthquake, for example, 3 others, that's the minimum, where these circles cross, that is where the earthquake originated from. Now, the more stations that record the earthquake, the better the location. For example, this is the northern Wheatbelt, and this is the earthquake swarm around Beacon of 2009. There were over 270 events in an 8-month period. If we look at the locations given by Geoscience Australia from the national network, they appear to lie in a linear trend. Now, is this trend real? Can we compare it to the geology? Let's have a look at the geological map. You see a lot of it's pink, that indicates a granitic rock, but most of it's covered by this yellow stuff, indicating this is soils obscuring the rock, so it's a bit hard to say. We can use remote sensing methods. Now, this is an example of total magnetic intensity. We see a lot of linear trends here. These are dikes, and we see the granite here. Maybe this is a different granite, or maybe it's just where the granite is covered by soils. But anyway, we can try and correlate the location of the earthquakes to where the granites are, to the geology. There is a private network working in the same area, and this added its pics of the P and S waves to the GA data, and it's managed to locate these cluster much more in a pinpoint rather than in a linear trend. So this gives an example of when you add more detections to an event, we can really start to pinpoint where these events are coming from. This has quite a bit of implications for when we look at building new infrastructure. We really need to know where these points of seismicity are. Other projects that the Geological Survey has been involved in is temporary arrays. Now, these tend to look at whole Earth structure. We're trying to investigate the structure of the ground beneath that array. We've had an exciting project down in the Albany Fraser, one in the Gascoyne, a more recent one in the Canning Basin, a high resolution one in the Eastern Goldfields, and then one which was looking at recording earthquakes in a very noisy environment in the Perth Basin. So all this data that the GSWA accumulates is all reported through our e-bookshop. So if you're interested in any of the work we're doing, please go to the e-bookshop and look up some of these references. So here are some references for interesting reading on our work and other people's work that I've talked about as I've been through. So I hope you found that interesting, and follow our website for more details, because we are doing more work in this area in the near future.